Before we go about building an intuitive understanding of what electric field is, let's do the mathematical definition of the field. Let's go to space and think that there is some charge present in space, a point charge q. I want to go to an arbitrary point P, which is some distance r away, and the unit vector would be in that direction, connecting the two points. At that place, at this point P, I bring in a test charge. The test charge is, so I bring in a test charge, let's call it Q. This Q is a test charge and is always positive. What is a test charge? Think of, I want to go and measure something. Go back to measuring a circuit, for example. What would you do? You would bring a probe. Let's say I want to measure voltage across a line. You'll bring two probes. You'll put one on the ground, one on the line. So you have to somehow probe the system to be able to figure out what the system is doing. That's what we are doing with this test charge. We have a system with charge Q present, and to probe what this charge Q is doing at point P, we are bringing this test charge. And by definition, the test charge has to be always positive. This Q can be positive or negative, doesn't matter. But this small q, which I'm representing it for test charge, that by definition has to be always positive, and the electric fields we are going to define are going to be defined with respect to a positive test charge. So if I break the charge here, what would this charge see? This charge will start to feel a force happening on it, and the value of the force, simply by Coulomb's law, is the Coulomb's constant multiplication of the magnitude of the charges divided by the distance square, which is r square. We define electric field E as force per unit test charge under the limit that the test charge is very, very small. This is the mathematical definition of the electric field. The force per unit test charge I bring in, so if I bring in a test charge of +1 coulombs, the force which I would feel at point P would be the electric field at that point P. We do limit the fact that this test charge is very, very small, so it does not go and perturb the system itself, both in its value and in its dimension. It is like a point test charge. And if we just put the terms up there, the equation is pretty simple. Q will cancel out, and the electric field E, due to this capital Q, will simply be KQ r square by r hat. Does it look like we have done much different than what we have been doing? If, on the other hand, now let's say you want to bring in a new charge there, let's call it Q2, then the force which will happen on Q2 would be, if I just use Coulomb's law, KQ2 Q by r square r hat. And if you notice this, I can write it as kq r square r hat q2. And this just becomes q2, the field which I have at that point. Almost looks like the same thing we have done before with Coulomb's law. But instead of doing stuff in one step, we are doing stuff in two steps. We are doing this calculation in two steps. First, we are saying that the field due to charge Q at that point P is given by kq by r square, and this field is interacting with the charge which I put at that point, and when it interacts with the charge, it creates a force, and the force is equal to the charge I put in at point P multiplied by the electric field. So effectively, while mathematically we don't seem to have done anything new, philosophically there is a big change. Philosophically, what we had before in Coulomb's law was the fact that if I have two charges present, there is a force at an action at a distance which happens, and there are forces which are created which I can calculate. Let's call this 1 to 2 and this 2 to 1. We can calculate these forces as simply, for example, F1 to 2 would be KQ1 Q2 by R square R hat. We're calling this direction to be R hat. Now we are saying philosophically that I have a charge Q1 which is present here. This charge doesn't necessarily interact with other charges around it, but what it does is it creates a field, and that field starts to be distributed in space. So around this charge you create a field which is your E. I'm representing the field by a vector, the direction telling me the direction of E, and I'm representing the length of the field, the strength of the field by the length of the vector for the time being, and we'll see how to visualize it later. But now what is happening is when I bring in another charge at some point P, Q2 at point P, then the force which I will see at charge Q2 is not because this charge Q2 is somehow interacting with charge Q1 at a distance, but this charge Q2 is relating to the electric field due to charge Q1 at that point. So the electric field, whatever is the electric field at that point, let's call it EP, due to Q1, this charge Q2 interacts with that field, and in interacting with that field, it feels a force which is Q2 EP, where EP again is going to be due to what is created by charge Q1. Mathematically, there doesn't seem to be any change. Philosophically, we have changed it a lot.